Okay, good afternoon. It's time for us to get started. So before you get into the material for today, I wanted to clarify some questions that I got from some students this morning during my office hours. Um, there were questions about one of the problems in the assignment. Specifically, I think was problem number 2. So I decided to extend the deadline for submission of the assignment because I didn't include the equations in the lecture material, the equations that you need to solve that problem. However, it is part of the lecture material in terms of the reading material for the class. If you look at section 10.5.2 in efficiency, that's part of the discussion of the material we covered last time for push and comparison of COMWIP and MRP. They explain the scenario that is presented in problem number 2 in the assignment. So here we have a 5 single machine stations, each station processes job at a rate of 1 per hour. So they have the same processing time. And then this system, the throughput of the COMWIP system is a function of the WIP or the WIP area is given by the formula of the practical worst case from chapter 7, which the problem is also making reference to. So that throughput can be computed using this formula. And also they provided an expression for the average WIP, which is as presented here. So these are the same equations that we discussed. They're just simplified for the scenario that is presented in the question. So the VUT equation, for example, can be simplified to get this expression. So in this case, they have 5 machines and they're computing again, same processing time. So, and these are managed as an MM1 queue and independently, each one of them. And that's why you can compute based under those assumptions, you can compute the average WIP as the number of machines times the utilization divided by 1 minus the utilization. Okay, so I'm gonna place this slide also as part of the lecture from last week. In case you want to go over those, again, it's part of the textbook, chapter 10 for the COMWIP systems. And hopefully this can help you solve the second question in the assignment. What else? The other announcement I have is I graded the labs and the project reports. So you should be able to see your grades right now. I saw some problems with some of the students' reports. The idea of collecting the data and analyzing the data was that you were able to develop some probability models that were useful for studying your system. So if your probability models are not giving you a p-value for both tests that is higher than 0.05, then those probability models are not good. So you have 2 options. You can collect more data and then try to fit the models to that data. Yeah, actually and then the other option is just to figure out if you can manage the number of intervals in your histogram to try to accommodate a better fit. So submitting productivity models that were not presenting a good fit, that was bad. So I took points, and also there were some reports that didn't provide a group of performance measures for validation and verification. So that was another important piece of the report, because that's the numbers that you're going to use for verification and validation of your simulation model, the simulation model that you're going to present at the end of the semester. So if you were facing those problems, then you have more work to do. You might need to go and find, get more data and try to fix those probability models. And also get some additional data for computing the performance measurements that you're going to use for your validation. Those two things will be important for your final report. Any questions?
Hi, Professor.
Okay, so let's move forward. The next topic that we have for today is the total quality manufacturing. So today we're going to look at some of the quality aspects of modeling manufacturing systems. And the agenda is the following. We're going to provide an introduction, and then the views of quality will be discussed. We're going to talk about what's statistical quality control, Six Sigma, and also the relationship between quality and operations. So there's a quote, say quality is not an act, is a habit. So something that you have to do continuously in order to reach a certain level. So let's look at the introduction. We've been discussing the topic of variability in terms of manufacturing systems for a long time now. So we know that variability plays an important role in determining the performance of the manufacturing systems, and that it can come from different sources, and those sources are listed in this slide. So we have talked about the failures, the importance of accounting, the difference between short failures versus long failures, and the impact of the frequency also of those failures and how those affect the performance of your system, setups, operator behavior, and also different product families or different product mix. So a particular important source of variability which can radically alter the performance of a system is also the quality. So quality is something that we can measure, and it will depend on the type of product or the service that you're providing. And variability reduction is frequently a vehicle for us to achieve improvement in terms of quality. So in terms of these studying quality, there's two major categories in terms of the literature for this particular subject. One of them is called Total Quality Management, or TQM. This focuses on quality in qualitative management terms. For example, fostering an overall environment supportive of the quality improvement. And then there's the Statistical Quality Control, or SQC, which focus on quality in quantitative engineering terms, meaning that you're measuring and assuring compliance within certain specifications. So two different perspectives. One is focusing on the qualitative aspect in terms of management. So you're focusing on fostering an environment that will guide people to perform better. And then the SQC is looking at some measurements, a quantitative aspect of measuring quality and making sure that the bounds in terms of performance are met. So in terms of views of quality, internals versus external quality. Internal quality refers to conformance with quality specifications inside the plant or the manufacturing facility. And this is typically monitored through direct product measurements, such as the scrap or the rework rates. So we go to the manufacturing line and we check, okay, so you're producing this many items, how many of them are defective, how many of them need rework. If you're looking at the final product, how many of the orders are returned after a day, and you can keep track of those internal quality specifications. External quality refers to how the customers view the product. So is this a good product? If people are buying this product? And that's in terms of external quality. It can be monitored via direct measures of customer satisfaction, such as the return rate. So how many of these products are being returned? To achieve a high external quality, one must translate customer concerns to measures and controls for internal quality. And the following are some important ways in which quality inside of the plant is linked to the quality that results in customer satisfaction. So number one is error prevention. So we talk about the benefits of pull versus push, and I mentioned it many times that you have a better chance of capturing an error in the pull system versus the push system, because there's some accountability on the different stages in the process. So error prevention is the number one. If fewer errors are made in the plant, fewer defects are likely to slip through the inspection process and reach the customer. So we want to make sure that in every step of the process, we are keeping track of the quality of the product and minimizing the opportunities for or the chances to commit errors. And then that's the preventive option, right? This is more like a preventive type of approach. We want to prevent errors, want to minimize the errors, but we know some of them are going to appear at some point. So the next number two is inspection improvement. So now this is more like a reactive approach in which you are basically assuming that you're going to have errors at some point, and you want to have a good inspection process. So if fewer defects are produced during the manufacturing process, then quality assurance will require inspection to detect and reject or correct fewer items. And then three is the environment enhancement. So many quality problems experienced by the customer cannot be detected in the plant. So, so there will be things that even if you try to detect, might not show up. So for these and for problems that are observable but manage to slip through anyway, it's important to establish a feedback loop in which field information is used to improve internal processes. So these are the things that we do when, for example, you purchase a electronic and you get this card that asks you to register the product. So if you do that and then you face problems with it in the future, you can tie your complaint to that registration of that particular product. Quality registration is another thing. Like if you are able to get your customer to register for for warranty, then you have a loop in which you can measure the quality of your product. And that helps you to improve your environment. Okay, so those are views of quality. We talk about the internal versus external quality. Now we can move into what is statistical quality of control. So if you are in industrial engineering, or if your background is in industrial engineering, you might have a class or a course on statistical quality control. And the idea here is that you use some statistical tools to track the quality of processes. And then those tools are helpful in terms of understanding the processes that are happening, whether or not they're processing parts at the expected efficiency in the process, and so on. So statistical quality control focuses on manufacturing quality as measured by conformance to specifications. And the ultimate goal of statistical quality control is the systematic reduction of variability in key quality measures. So we're going to focus on specific, for example, the size, the weight, the smoothness, the strength, the color, and the speed of delivery, for example. These are all measurable attributes that can be used to characterize the quality of a manufacturing process. So again, maybe we can choose 2 or 3, but most of the time we're focusing on a specific attribute of the product, which is the one that is most likely to create a particular defect, for example, in the product. So if you know that you have a process that is not very reliable, or a machine that might be not so new that is creating problems in the process, then you'll find that specific attribute that is going to match that performance in order to see whether or not there's a problem with your process. So statistical quality control approaches, we can classify the tools used in statistical quality control to ensure quality in 3 major categories. Okay, so first, the first one is called acceptance sampling. Here, products are inspected to determine whether they conform to quality specifications. So the idea here is that you don't test every single item. You have a sampling mechanism or structure in place. For example, you have time periods in which you're gonna go grab some of the product from an area, and you're gonna go perform a test on those. It's random. And you're gonna see whether or not these products that you are collecting during your sample or sampling are passing those quality specifications. In some situations, 100% inspection is used, while in other some forms, statistical sampling is substituted. So here I have two different examples. So for example, cell phone plants typically subject every unit to a cycle of automated tests to ensure that circuits and control function properly. So in this case, you will have a test that is performed on every single item in your process. In contrast, a candy factory cannot subject every piece of candy to a taste test, and so must rely on periodic sampling to ensure quality, right? So in this other case, you're basically going into the process, collecting some samples following a specific protocol, and then using those samples, you're gonna extrapolate in terms of the quality of a larger amount. So note that acceptance sampling is essentially an end-of-line method, which can find problems only after they have occurred. So for this type of sampling or acceptance sampling, you're waiting until the product is already completed in order to make a judgment of whether or not it is of good quality. So the second approach is called statistical process control. And in this one, processes are continuously monitored with respect to both mean and variability of performance to determine when special problems occur and when the process has gone out of control. So in this, you're basically keeping track of all the items that are going through a specific process, or maybe a sample per batch. So let's say you have a batch of 100 parts. You perform you get a sample from that batch, and you perform the test on that sample, and then you judge that lot based on that sample. But you have a continuous monitoring with respect to the mean of that process and the variability. Note that this statistical process control is a real-time method which identifies problems as they occur or very shortly afterwards, and so facilitates rapid remediation. So in this particular strategy, let's say you are looking at a manufacturing process, a manufacturing line, and you have this, might not be the only process in which your product is going to be involved, but you're continuously monitoring this process. And if you know that at some point the process goes out of control, you can perform some remedial action before those parts are moved into the next step. So this facilitates rapid remediation. So for example, here we have a nickel plating process. It is important to monitor and adjust temperature, pH, and constituent levels in the chemical baths. So in order for you to get this product looking like this, you have to continuously keep track of these parameters. If these depart from the desired levels, quality problems, for example, poor finish, adhesion, or durability may result, and so corrective steps must be taken. So if you are looking at the process, you're continuously keeping track of these three parameters. In addition to tracking chemical process parameters, it is also common to monitor the plated product directly. So for example, once the product is completed, you can go check on the thickness of the coating. Again, if plating thickness depart from the desired level, then you can perform some corrective action. The third option is what we call design of experiments. So again, within industrial engineering, we have courses talking about quality control. We have courses in most of these three aspects. Sampling is discussed as part of courses, statistical process control and reliability. And we also have a class on design of experiments. So this third strategy or approach causes quality problems are traced through specifically targeted experiments. So the basic idea is to systematically vary controllable variables to determine their effect on quality measures. So if you have a process and you have temperature, you have, I don't know, water pressure, you have the all the different components, and you're keeping track of the levels of each one of these variables, and then you can perform experiments to see what will be the impact of these variables in the product. A host of statistical tools, for example, block designs, have been developed for efficiency or efficiently correlated controls with outputs and optimizing processes. Note that the DOE or design experiment is a diagnostic tool which identifies the causes of problems and thereby helps prevent future occurrences. So this is the third approach. So for example, for design of experiments, John Deere Engine Works use DOE methods to investigate the effects of chromate conversion, paint type, and surface treatment on paint addition to aluminum parts. They discovered that paint type was the major determinant of addition and we're able to save $500,000 per year by eliminating chromate conversion. Okay, so that's just an example of the impact of these type of approaches. Identifying the effects of these variables and then being able to eliminate those that have no impact whatsoever in your product. So going back to statistical process control, this generally begins with a measurable quality attribute. So you have your product and you want to see whether or not you're achieving the specific level of that parameter. So for example, the diameter of a hole in a cast steel part. A process that is operating stably within its natural variation is said to be in statistical control. So essentially what you have is a plot that is showing you two bounds that are saying, okay, if you are within these bounds, your process is in control. But if at some point you are outside these bounds, you have to monitor whether or not you're going to continue being outside those bounds. That means that your process could be out of control. So larger sources of variability can potentially be traced to their causes called an assignable cause variation, and a process subject to assignable cause variation is said to be out of control. So the fundamental challenge of statistical process control is to separate assignable cause variation from natural variation. So we talk about natural variation, right? Those are the variability that is in the process. It's not something that we can control, but separating that from an assignable cause is difficult. So consider the example of controlling the diameter of a hole in a steel part made by a sand casting process. Suppose that the desired nominal diameter is 10 millimeters, and we observe a casting with a diameter of 10.1 millimeters. Can we conclude that the casting process is out of control? Would you say that that's a reason to say this is out of control? I'm asking you guys. Would you say?
It depends on the parameter of what we assume. Like, can we assume the tolerance limit will be like 0.1 or 0.2? It depends on that.
Okay, so the comment or the argument is whether or not this is outside the tolerance of the product, right? And I think that's right. So it's impossible for you to reach a specific measurement every time. So you have some tolerance for your product. That's correct. Another thing that we, as I mentioned already, you have to continuously measure these variables to make a judgment on whether or not you are in control. If it's something that is happening just once and then it's not happening again, then is okay. But if it's something that is increasing and is happening often, then you have more reasons to believe that your process might be out of control. So the answer, as you said, it depends. It may be a deviation of 0.1 millimeter is well within the natural variation levels, or also within the tolerances. So if this were the case, then we were to adjust the process by altering the sand steel in an attempt to correct the deviation, in all likelihood will make it worse. The reason is that adjusting a process in response to random noise increases its variability. So if it's something that is associated with the natural variation levels, then we shouldn't worry about. Hence, to ensure the adjustments are made only in response to assignable cause variation, we must characterize what's the natural variation of the process. So suppose we have measured a number of castings and we have determined that the mean diameter can be controlled to be equal to 10 millimeters, and the standard deviation is 0.025 millimeters. Further, suppose that every 2 hours we take a random sample of 5 castings, measure their hole diameters, and compute the average, which we call X bar, and plot it on a chart. Something like this. So what we are doing, okay, we are looking at the process. We are not measuring every single item, but we are doing a sampling. And every time we go do the sampling, every 2 hours, we get 5 units. We measure and we compute the average. And then we plot the average on this chart. So for example, we have the sample number here at the bottom. We have the X bar, which is the average, and we are plotting the X bar. Those are the dots that you're seeing in the plot. So this is showing the graph. As you can see here, we have the expected measurement is 10. The variability is there, right? And there's points that go way beyond this area. You see, some of them stay within the same region, but there's some of them that are going way down or way up into those levels. So in general, and you'll see that in a few minutes, what we typically do, in addition to compute the X bar, is to compute those UCL and those LCL values, which stand for upper control level or upper control limit and lower control limit. And those are helpful in understanding the natural variability of our system. We know if our measurements are within these control levels, then our process is okay. But if you see a large deviation from those, then we have cause to investigate this variation. So statistical process control. This is from basic statistics. We know that X bar is itself a random variable that has a standard deviation. So we can compute the standard deviation for this random variable, X bar. So remember, X bar from our previous example is coming from a sample of 5 items, right? So by doing the computation only in that sample, automatically you know that's a random variable. The basic idea behind control chart is very important to hypothesis testing. So we typically assign our null hypothesis to the process is in control. That is, the samples are coming from a process with a mean and a standard deviation. And those values are for the population, right? Mu and sigma. When you use mu, you're talking about the population. When you use X bar, you're talking about a sample. Same thing for sigma. This is for the population. Sigma X bar is for the sample average. So to avoid concluding that the process is out of control when it's not, that's type 1 error, we set a stringent standard for the designating deviation as assignable cost. Standard convention is to flag points that are like more than 3 standard deviation above or below the mean. We do this by specifying a lower and upper control limit as follows. So our lower control limit will use the population mean minus 3 standard deviation of the average of the mean. The upper control limit is the same population mean plus 3 times the sigma of X bar. Those are the equations that we use to compute these limits that you can see in the bar and the chart. Yes. Yes.
They using the mean of population, but they uses a sigma from the sample function.
Yes. So that's a good question. So again, these formulas are coming from a, they're just not coming out of nowhere. They come from a series of steps that make some assumptions, and those are typically explained on the statistical books. But the idea is that, remember that you want to stay as close as possible to that target measurement, right? And that target measurement is what's given by mu, right? You want the population mean to be this target measurement. And then the deviation plus minus 3 sigma, sigma of the random variable of the sample, which is coming from the actual process. All right, so the variability that you're observing from the actual process. So you have a target measurement, and then you're adding the deviation from the actual process. Also, knowing that mu parameter, that target measurement is part of the design, right? But in order for you to get the standard deviation of the population, you will have to test every single item in the production. So, which is very difficult to do. So we compute the standard deviation of the samples. And then if we go outside those limits, we find if there's an assignable cause of variation, and then we can perform some corrective action to get the process back in control. So you can see that in this example, there's a deviation occurring here in sample 22. So that goes very, very low here. And then there's another point here that says auto control mean shift. So here's an example, statistical process control. Suppose in our casting example that for reasons of functionality, we require the whole diameter to be between a lower specification level and an upper specification level. Whether or not the process is capable of achieving this level depends on how they compare with the lower and upper natural tolerances limits, which are defined as here. So here we have the sigma for the population, and instead of the sigma of the sample. Note that L and TL and U and TL are limits on the diameter of individual holes, while the lows LCL or UCL are limits on the average diameter of the sample. So so the difference here is that one is considering the sample and the other one not. Moreover, note that the L and TL and U and TL are internally determined by the process itself, while the LSL and USL are externally determined by the performance requirements. So let us consider some illustrative cases. The natural tolerance limits are given by LTL, NTL equals mu minus 3 sigma. So in this case, mu equals 10, sigma equals 0.025. And then we have those equal to 9.925. The limit natural tolerance limit is 10.075. Suppose that the specification levels are given by LSL equal LSL1, 9.975, and USL equal to 10.025. So here we have the process capability comparing specification limits to natural tolerance limits. We see at the bottom values that we just compute. So here's the LSL1, USL1. They are closer to the mu value. And then those UNTL are closer to the variability observed to the process. And the LSL2, USL2, those we have not computed those yet, are outside the variability of the process. So you can see the difference between them. If you are using those natural tolerances, you have more space to accommodate your product measurements. Whereas if you are using the LSL, those are closer to the mean. So it's apparent from figure 12.2 that the casting process will produce a large fraction of non-conforming parts. To be precise, if all diameters are normally distributed, then for us to be within those bounds, right? I'm sorry, we go back here. So if we want to be within those bounds of 9.97 and 10.025, these two bounds, probability that the X is going to be within those, assuming that these diameters are normally distributed, is going to be very low, 0.3174. Because we know there's a large amount of observations that are outside these bounds. This means that almost 32% will fail to meet specification levels. Suppose instead that the specification levels are given by LSL2, which are 9.8975 and 10.125. Since the natural tolerance limits lie well within this range, we will expect very few non-conforming castings. So if we repeat that process again, meaning that instead of being here now, we are here, we know that most of those are going to be inside, so the probability of non-conforming will be very small. So a measure of capability is the process capability index, which is defined by this CPK, and that's equal to Z, or that probability, that normal probability, standard normal probability minimum divided by 3, where this Z-min is the minimum between the Z minus Z value for LSL and the Z value for USL. And this Z value is again computed using this transformation for the standard normal distribution, in which you take the value of the limit, you subtract the mean, and you divide by the standard deviation of the population. Same thing for the upper. So you compute these two, you look at the minimum, and then you can compute the process capability index. The minimum acceptable value for the CPK value is generally considered to be 1. Note that in the above example, CPK equals 1/3 for LSL1 and USL1, but CPK equals 5/3 for LSL2 and USL2. It gives us a simple quantitative measure of how capable a process is of meeting the performance specifications. So if you set up your limits to LSL1 and USL2, you'll see that there's based on the CPK, you might not be, or the process might not be able to achieve meeting that performance specification, because it's less than 1, it's 1/3. But for the other one, 5/3 is greater than 1, and we are more capable of meeting those specifications. Some extensions for statistical process control. The X bar chart discussed is only one type of statistical process control chart. Many variations have been proposed to meet the needs of a wide variety of quality assurance situations. So for example, there's the range R charts. This is an X bar chart, requires process variability that is sigma to be in control in order for the control limit to be valid. Therefore, it is common to monitor this variability by charting the range of the samples. If X1, X2, up to Xn are measurements, for example, the hole diameters in a sample of size n, then the range is the difference between the largest and the smallest observation. Each sample yields a range, which can be plotted on a chart using part data to estimate the mean and standard deviation of R, denoted by R bar and sigma R. We can set the control limits for the R chart as follows. So this is an alternative, because as we mentioned, this bar chart, X bar chart, requires the process variability sigma. So sometimes getting that value is difficult. So we can rely on a different strategy. This one considers the range. And then we have the fraction non-conforming P chart. This is an alternative to charting a physical measure, as we do in an X chart. We track the fraction of items in periodic samples that fail to meet quality standards. Note that these standards could be quantitative or qualitative. If each item independently has a probability P of being defective, then the variance of the fraction of non-conforming items in a sample of size n is given by this equation, P times 1 minus P divided by n. Therefore, if we estimate the fraction of non-conforming items from past data, we can express the control limits for the P chart as here. We have the fraction of non-conforming parts, which is P, minus 3 times this variability, which is the square root of P times 1 minus P divided by n. Okay, so those are different options for statistical quality control. Now, the next topic on the agenda is Six Sigma. And I know some of you are familiar with this methodology. Actually, we have a certification. It's gonna be offered by the IISc chapter. If you haven't done that certification, it's gonna be offered now in April, in third weekend of April. It's gonna be virtual. So if you are interested in getting that certification, you can contact me and I will put you in touch with the chapter. So Six Sigma is a model that links process variability to defects. So as we noted in figure 12.2, the fraction of non-conforming outputs depend on the specification limits. The larger the interval, the smaller the likelihood of a non-conforming output. So the larger the space for you to not fail, the smaller the likelihood of non-conforming. So the Six Sigma model measures the specification interval in units of sigma and uses the normal distribution to compute the expected number of non-conforming outputs. So we go back to our example. Suppose that we have determined that a casting is usable as long as the diameter is between 9.95 and 10.05 millimeters. In statistical process control terms, this means that the specification interval is by LSL USL 9.95, 10.05, which has a half width of 0.05 millimeters. Suppose further that the casting process produces casting whose diameter is normally distributed with a mean of 10 millimeters and a standard deviation of 0.025 millimeters. We call this a center process because the mean of the actual process is directly at the center of the specification limit. Furthermore, since the half weight of the specification interval is equal to 2 standard deviation of the process, 2 times 0.025 equals 0.05 millimeters, we call this a 2 sigma process. If the specification interval were 3 standard deviations wide, then those limits will be expanded, and then this will be a 3 sigma process. And if we expand this to 6 sigma, this will be the bounds for a 6 sigma process. So the idea is that you determine those bounds for meeting the specifications based on the number of sigmas. So here we have different plots comparing the plots for the different sigma values. So for example, here, let me use my pen. So here we have the center, right? And we have a 2 sigma limit. So here, and this is for the center process. So for the center process, only 4.6% will be non-conforming, right? So that will be this and this. But that's assuming that we have a center process, right? If that were not the case, let's say we have a process that is shifted by 1.5 sigma, which is the other plot. This plot right here. If we set up our limits to be 2 sigma, then we know that all this will be non-conforming. So for a shifted process, that will be 30.9% of non-conforming parts. And what the plot is showing is, as we increase this to 3 sigma, that shifted process will observe a smaller amount of non-conforming parts. And this is the case for 6 sigma. You see that these two numbers are not very different. So the 6 sigma methodology is basically saying that this should be the maximum level of tolerance that you should accommodate. If you are outside the 6 sigma, then you have space for improvement. So here's non-conformities per million opportunities for various sigma values. So you see here the differences in defects in parts per million. So if you are at 1 sigma, you see the number of defects in parts per million is very high. But if you move to 6 sigma, those values are pretty low. So the 6 sigma is a reasonable way to measure relative quality improvement progress, provided the number of potential opportunities for defects is fixed. It does not provide an absolute comparison of quality between different systems. So this is a way for us to make sure that we are within the conformance of the process. The real substance of Six Sigma lies in the framework and tools developed to achieve the above statistical quality standard. Basic framework is which the quantitative tools of Six Sigma are used to drive quality towards the 3.4 parts per million defect rate is called the DMAIC, which stands for define the process to be improved, measure current performance, analyze when, where, and why defects occur, improve the process by eliminating defects, and control process performance. So when we say 3.4, this is the number that we're referring to for Six Sigma when the process is shifted. So if we want to drive our quality to that goal, then the DMAIA strategy is what's behind the lean methodology. This is also, like, for those of you who are planning to interview, you don't have knowledge about Six Sigma. When you go for an interview, you can try to answer these problems, subjective questions that are formulated in your interview using this strategy. Most of manufacturing companies that are good in Lean or Six Sigma, they look for answers that follow this DMAIC method. So if they present you with a problem, you can address the answer using these 5 steps. So that's an advice from experience. So you face the question, we have this problem, how would you address this problem? You can say, well, first thing I would do, define the problem, process, and then measure the performance. And typically that's what they're looking for. For processes that do not yet exist or in need of substantial redesign, variant of DMI called DMI DB is appropriate. It's the same idea. Define the goals for the project, measure, determine customer needs and specifications, analyze the process options to meet the customer needs, design the process to meet the customer needs, verify the design performance in terms of its ability to meet the customer needs. So again, this is for a process that might not exist yet, or is a variant or a redesign. Questions? Now, one more thing to discuss, which is quality and operations. So variability is one important link between quality and operations. The other link is cost. However, there is some disagreement about just how this link works. 2 distinct views follow. One is the view that says that cost increases with quality. This is the traditional industrial engineering view, which holds that achieving higher external quality requires more intense inspections, more rejects, and more expensive materials and processes. The other point of view is the cost decreases with quality. This is more recent TQM view, exposed using phrases such as quality is free or hidden factory. It holds that the material and label savings from doing things right the first time more than offset the cost of the quality improvements. These views support the 0 defects and continuous improvement goals of just in time. So these are typically the 2 views that you will see in practice. As illustrated in figure 12.4, this dynamic results the total cost of quality, including both prevention and failure costs, decreasing and then increasing in the yield. So, so here we have a graph, cost versus yield. So if you have a certain amount of output, right, gets to a point in which you have to invest more resources to achieve certain amount of prevention. And there will be a point in which that cost, doesn't matter, you're using it for prevention, will go up. And then if you're looking failure costs, typically that will be pretty high. The yield is low, and then as you move forward, it will go down. And then the total cost will look like, we call this the bathtub plot, right? So it looks like a U, and you see there will be meeting here in the middle, but they will be high at different points of the yield. Failure cost is very high at the beginning. Especially if you're working with a new product, you move forward. And then once the product is well known, you increase your output. At some point, the prevention will increase. Quality supports operations. We presented two manufacturing laws that are central to understanding the impact of quality in plant operations, the Variability Law and the Utilization Law. This can be paraphrased as follows. Variability causes congestion, and congestion increases non-linearly with utilization. In practice, problems or quality problems are one of the largest and most common cause of variability. Additionally, by causing work to be done over, quality problems often end up increasing the utilization of workstations. So for rework and so on. So by affecting both variability and capacity, quality problems can have extreme operational consequences. So the effects of rework on a single machine. Consider a simple single machine example shown here. The machine receives part at a rate of 1 every 3 minutes. Processing times have a mean and standard deviation of T0 and sigma 0 minutes, so that the coefficient of variation of the natural process time is C0. However, with probability P, again, part is defective. So when there's a defective part, if you can see here in this simple graph, that part might need to return to the process for rework. So we assume that whether the part is defective is immediately known upon its completion. If it is defective, it must be reworked, which requires another processing time with mean T0 and a standard deviation sigma 0. And again, it has a probability of failing. The machine continues reworking the part until a good one is produced. We define the total time it takes to produce a good part to be an effective processing time. So it will depend on how many times you have to go through this loop. Letting TE represent the random effective processing time of a part, we can compute the mean TE variance sigma E squared and square coefficient of variation of this time, as well as the utilization of the machine U as follows. So these are the equations that we can use to study these type of systems. So we have a law, rework law. For a given throughput level, rework increases both the mean and standard deviation of the cycle time of a process. You have more work. So to give an illustration of this law, suppose the previously mentioned station is fed by a modularly variable arrival process, but has deterministic processing time such as T0 equals 1 and Z0 equals 0. Then for Kinsman model of a workstation, the cycle time at the station can be expressed as a function of P. So, so we are now looking at the BUT equation here, but using the P probability of rework as part of the, or reformulating the BUT equation using that probability of failure. And we can compute that using this function to compute the cycle time. And again, this is based on this example in which we have an arrival rate of 1/3. And the processing time is not known. This term is T0. So this is the cycle time as a function of the rework rate using that expression. And you can see as you increase the rework, the cycle time will also increase, which makes sense, right? So if no rework, cycle time is very low. If you have a 50% chance of rework, that cycle time is going to start increasing. After 60, it will go up really quick. Here's the throughput versus the working process for different rework. So these are the probabilities of rework. And you can see how the throughput goes down as, I'm sorry, the throughput, yes, goes down as we decrease the probability of failure. Go up as we decrease the probability of failure. Cycle times, we're going to stay in the same dynamic. For a high P, a higher cycle time. And that's the last slide. Questions, comments? Good. So, so that's all I have for today. On Monday, we're going to meet to work on our next lab assignment and methods. And there's an assignment based on this material on Canvas, so you can start working with that. And if you have questions, let me know. I extended the assignment for today that was due today until Friday. So I'm gonna post that material that I showed you at the beginning of the lecture on the slides for Monday. You can look at those equations and let me know if you have any questions. Not then I'll see you on Monday.
Hey, and Dr. Perez, I got my index problem solved, so I don't need to go to the later office hours today too.
Okay, great.
Okay, thank you,
Thank you for
Dr.
letting me
Perez.
know.
Thank you.
Thank you.